Hello everyone, today we're going to be discussing the problems from yesterday's competition. So we're going to go over the problems that Professor Lowe did not go over today in the morning. So we are going to start soon. Okay, now let's begin. Find the value of 16 to the power of 1 over 1 plus 1/3. So, in order to solve this problem, the idea is you just do 16 to the power of 1 over 1 or 4/3, which is equal to 16 to the power of 3/4. And since 16 is 2 to the power of 4, this is going to be equal to 2 to the 4 to 3/4. And the 4's will cancel, or we're left with 2 to the 3, which is 8. So 8 is the answer to this question. Okay, now let's continue. Mark rents a car which has a booking fee of $200 and has to pay $75 every week. When he returns the car, he pays an additional $500 for vehicle damage, and the total expenses are $1,450. How many weeks did he rent the car for? So this problem, you just set up a simple equation. You have 200 plus 75 times the number of weeks, let's say W, plus 500 equals 1450. And now we have 75W equals 750, or W equal to 10. So next problem, Poshino already went over it. So the idea is you just do 45 seconds of eating. So 45 seconds of eating, 45 seconds. And then a 15-second break. And then 45 seconds more of eating. And then, so this is the eating time, the red ones are eating. And then another 15-second break. And then 30 seconds of eating. So in total, we have 45 plus 45 plus 30 equal to 120 seconds of eating. And each second he eats 3 cookies, so 120 times 3 equal to 360, which is the answer. So for number 4, so the idea here is you look at the number of powers of 7 in this, and this, in all 3 expressions. And then, so if you remember from the previous class, one of the previous classes, we just find the number of factors in each of these terms, and we can do that using the trick. So how many multiples of 7 are less than 87? Well, that's going to be 87 divided by 7. 87 divided by 7 is 12, excluding remainders, of course. But then there's also some numbers which are multiples of 49. And there's 87 divided by 49 equal to one of those numbers. So in total, 87 factorial has 13 factors of 7. Now for 72 factorial, we have 72 divided by 7 equal to 10, and 72 divided by 49 equal to 1. So in total we have 7 to 11 here. And then for 36 factorial, we have 36 divided by 7 equal to 5. And again, 36 factorial has no numbers that are multiples of 49 less than 36. So that means there's going to be no numbers which have 2 factors of 7 in it. So this is just going to be 7 to the 5. So overall we have 7 to the 13 times 7 to the 11 over 7 to the 5, which is equal to 7 to the 19. So the answer is 19, because we want n. Now let's take a look at the next problem. John has 9 red apples and 3 green apples. He randomly selects and eats an apple. So 9 red, 3 green. Then 3 of the red apples get rotten and are thrown away. And from the remaining apples, he randomly selects and eats another apple. If the probability that both of the apples are red is A over B, find A plus B. Okay, so for this problem, what's the probability of getting a red apple in the beginning? Okay, so we have 9 red apples, 3 green apples, so the probability of getting a red apple in the beginning is just 9 over 9 plus 3, which is 12. So 9/12 chance of randomly choosing a red apple in the beginning. But then here's the trick of this problem. We have 9 red and 3 green problems. Sorry, I don't know why I drew blue. So we have 9 red and 3 green apples in the beginning, but then he eats 1 red apple, of course. So if he eats 1 apple, we're left with just 8 red and 3 green apples, right? And again, the reason I'm doing this is because in order we want to find the probability both of the selected apples are red. In order to get both apples to be red, the first one has to be red and the second one has to be red. And again, we found the probability the first one is red to be 9/12. The probability the second one will be red, well, again, after eating one, there's only 8 red and 3 green apples left. But then 3 of the red apples get rotten, so we're left with 5 red and 3 green apples. So the probability of randomly selecting a red apple now to eat, because we want both of the apples to be red, not just one of them, is 5/8. And this simplifies to 3/4 times 5/8, which is 15/32. And then a plus b is just going to be 15 plus 32, which is 47, which is the answer for this problem. Now let's move on to the next problem. What is the remainder when 2 to the 20 minus 1 is divided by 7? So you remember from the digit cycle class earlier, we can just look for a pattern. So 2 to the 1, what is the remainder when 2 to the 1 is divided by 7? That's just going to be 2, of course. What about 2 squared? 2 squared will, of course, leave a remainder of 4 when divided by 7. 2 cubed will leave a remainder of, well, 2 cubed is 8, and 8 leaves a remainder of 1 when divided by 7. So 1, or I shouldn't say equal to, I should say, I'll draw an arrow there. 2 to the 4 will be 2 cubed times 2, so it's going to be 1 times 2, or 2. And now we can see that there's a pattern, right? So 2 to the 20, well, 20 leaves a remainder of 1 when divided by 3, so 20 will have the same, so as you can see here, every 3 cycles, every 3 powers of 2, we cycle. So 2, 4, 1, 2, 4, 1, so on. And since 2 to the 20 leaves a remainder of 1 when divided by 3, then 20 will have the same unit digit as 2 to the 1, which has a unit digit of 2. Right? Because now we're cycling 2019 powers of 2, and 3 powers of 2 get back to 1. So 2 to the 20 is 2, and then we have 2 minus 1 equal to 1. So the remainder when 2 to the 20 minus 1 when divided by 7 is just 1. Okay, so now let's continue. Josh went to a store with a number of dollars between 50 and 100, both inclusive. He spent a third of the money on lunch. He then tipped $15, and after that he deposited 2/3 of the remaining money into his bank account. After that, he donated a fifth of his remaining money to charity. He was then left with the integer number of dollars. How many dollars did he have at the beginning? Okay, so let's just say that he has M dollars in the beginning. Then we're given that he spends a third of his money on lunch, right? So if he spends a third of his money on lunch, he's left with 2/3 M. Because out of the M in the beginning, 1/3 went away to lunch, and he's left with 2/3 M. But then he tips $15. Right? He tips $15, so minus 15. And after that, he deposits 2/3 of his money into the bank account. So if he has some money left, he deposits 2/3 into the bank, and he's left with 1/3 of what he has. And that means we have 1/3 times 2/3 M minus 15. But then after that, he says that he donates a fifth of his remaining money to charity. And since he donates 1/5 of his remaining money, he's left with 4/5 of his original money. So we have 4/5 times this. This is going to be equal to, well, we can just expand this whole thing out. We get 8 in the numerator because 4 times 2. And in the denominator, we have 5 times 3 times 3, which is 45 M. And then minus, well, we have 4/5 times 1/3 times negative 15. So it's going to be equal to 4/5 times 1/3, which is 4/15, times negative 15, which is minus 4. So we just basically multiply this out. And we're given that he's left with an integer number of dollars. So what does that mean? Well, that means that this has to be, since this is an integer, right? This quantity will have to be an integer too. So if 8 over 45M is an integer, that means m has to be a multiple of 45. And as you can see, the only multiple between 50 and 100 is 45. I mean, it's 45 times 2, which is 90. So that means 90 is the answer. Now let's take a look at this problem. And just again, Professor already went over this, so let me just quickly recap what he said. So basically, you multiply all these out, and then we're left with a cubed times b cubed times c cubed times d cubed times e cubed. And then we get some quantity here, 4 times 6 times 12 times 18 times 9. And the idea is find the prime factorization of all the numbers. And then we're left with that this is going to be equal to 2 to the 6 times 3 to the 6. And since we want a times b times c times e, we just take the cube root of a, b, c, d cubed to get 2 squared times 3 squared, which is equal to 36, which is the answer. Okay, so for number 9, we're given that we have 2 quarter circles pieces, and we take off semicircles from them. And given that this big length is 40, meaning that this length here has 20. And what does that mean? Well, that means the radius of the quarter circle has to be 20. This is 20, this whole length, right? So we need to find the area of these two regions. We need to find the area of this region. We need to find the area of this region times 2, because these areas are equal, right? Okay, so if we need to find the area of this purple region, it means to multiply that by 2 to get the total area of this figure. Okay, so then, how can we find the area of this purple region I marked? Well, we can just find the area of the quarter circle, which is going to be pi times 20 squared divided by 4, which is equal to 100 pi, right? Because 20 squared is 400. Now what about the semicircular region? We need to subtract off the semicircle area. And since the diameter of the semicircle is 20, the radius of the semicircle will be 10. So we must subtract off pi times 10 squared over 2, which is 50 pi. So now from here, we see that the area of the purple region is just going to be 100 pi minus 50 pi, which is 50 pi. And now that we know the area of one of these regions is 50 pi, the area of both regions will be 2 times 50 pi, or 100 pi. Which is the answer for this problem. Now let's move on to the next problem. Okay, so for this problem, the idea is we want to drive 250 miles at a constant speed. But then he wants to reach in 5 hours, right? But then after driving for 100 miles, he takes a 30-minute break. And he continues driving at a speed that allowed him to arrive at the same time, even though he took a 30-minute break. We want to find how much faster he took. And actually, a common mistake on the contest yesterday was many people, they forgot how much faster he drove after his break. They just put how many miles per hour he was driving after the break. They forgot to subtract the original speed, 50 miles per hour. So make sure to remember what the question's asking. Okay, so in the beginning, we're given that 250 miles, 50 miles per hour, 5 hours. So he drives 100 miles, and he drives 100 miles, and he's driving at 50 miles an hour, so he's going to take 2 hours to travel 100 miles. 2 hours. Because he's traveling at 50 miles an hour. But then he takes a 30-minute break, so 30 minutes break, or let's say 0.5 hour break. So now he drives at a new constant speed that allowed that to arrive at the same time. So that means that would allow him to reach in 5 hours from when he started. Since he drove 2 hours and took a half-hour break, now he needs to drive 2.5 hours more and complete the remaining 150 miles, right? Since he drove 100 miles in the beginning. And then in order to find how fast he's driving now, we just do 150 divided by 2.5, which is, or 300 divided by 5, or 60 miles per hour. And again, now it's subtract off the initial speed. So 60 minus 50 miles per hour equals to 10. And now we're done with this problem. And again, remember here to read the question, understand what's going on, and make sure you remember faster. Alright, now let's move on to the next problem. And Professor Lowe also showed a backwards way to solve this problem, but I'm going to show you the forwards way, so directly going forwards rather than going backwards. So we have 7-step staircase. You can jump 1 or 3 steps forward in the beginning, and the last step 1, 2, or 3. Okay, so how many ways are there to reach the 0th step? So the number of ways to reach the 0th step is just going to be equal to, well, f of 0, right? We're defining the function f. So the number of ways to reach a certain step. So f of 0, the number of ways to reach the 0th step is just going to be equal to 1. F of 1, the number of ways to reach the first step, well, what is that going to be? Well, there's only one way to redo that because he just has to take a 1 step from the 0th step. F of 2, how can we get an f of 2? Well, again, there's no way other than taking a 1 step from f of 1. Because you cannot take a 2 step, you can only take a 1 or 3 step. So you cannot take a 2 step from f0. So f of 2 is just going to be equal to, well, 1 again. But f of 3, here's where things get a little bit tricky. F of 3 will be f of 2 plus f of 0. Because you can either take a 1 step or a 3 step. So f of 3 will be 1 plus 1 or 2. F of 4, or let me just write that out just to make it clear. So f of 4 will be f of 2 plus f of 0 equal to 1 plus 1 equal to 2. F of 4 will be equal to, again, a 1 step jump from f of 3 or a 3 step jump from f of 1. So that's just going to be 2 plus 1 or 3. And then again, f of 5 equal to f of 4 taking a 1 step jump plus f of 2 taking a 3 step jump. And f of 4 is 3, f of 2 is 1, so we're left with 4. F of 6, again, we're repeating the same process. We take a 1 step jump from f of 5 or a 3 step jump from f of 3, so f of 5 plus f of 3. F of 5 is 4, f of 3 is 2, we're left with 6. And f of 7, here's where things gets a little bit tricky. Now we can take a 1, 2, or 3 step jump. So you can either take from 6, 5, or 4, not just from 6 and 4. Now you can also take from 5. So now we just do f of 7 equal to f of 6 plus f of 5 plus f of 4, which is 6 plus 4 plus 3, which is 13, the answer to this problem. Okay, so now let's take a look at the next problem. Oh, this problem. So this one was a little bit tricky, and it's actually really easy to make a mistake on this problem. So this is a very complicated figure. So let me simplify it a little bit at first. So I'm just going to simplify the figure. I'm going to remove some lines. Let's just remove this whole line here. Let's remove this whole line here. Let's pretend that these lines didn't exist. We'll add them, but worry about them at the end. Let's also remove this line on the outside. We'll worry about it at the end. It's not to worry right now. Because now that we're not worrying about the other lines, now we just have this one figure here. So how many triangles are in this simplified figure? So how can we count this? So the idea here is we want to form a triangle, we have 6 of these lines. We have 6 of these lines. 1, 2, 3, 4, 5, 6, right? We have 6 of these lines. And in order to form a triangle, we must choose exactly 2 of them. And if you remember from the geometric counting class earlier, in order to determine a triangle, we must choose 2 lines. So if I blocked it by accident, here it is. Just to summarize, we just did direct recursion. And then we added up the previous values. We added up f of 6, f of 5, f of 4 to get f of 7. We added up f of 4, f of 5, f of 3 to get f of 6. F of 4, f of 2 to get 5, so on. We just did 1 plus 3. In the last case was special. We added 1 value ago, 2 values ago, and 3 values ago. And we got 13. Sorry about covering it, but let's move on. Back to this problem. We have 6 different lines that I drew earlier. We're ignoring the other parts, right? And in order to determine a triangle from these 6 lines, we must choose 2 of them, right? We have these 6 lines, and if we choose any two triangles, or any two of these 6 lines, let's just say we choose these 2 lines, for example. Oh, whoops. Let's say we choose these 2 lines. Sorry about that. Okay, let me just undo that. So let's just say that we choose these 2 lines. So after choosing these 2 lines, we've now constructed a triangle like this. So basically, any 2 lines we choose, they always determine a triangle. So that means out of these 6 lines, we have 6, choose 2 triangles. Because any 2 lines, including the base and the bottom, we now have a new triangle. So 6 choose 2 equals 6 times 5 divided by 2, which is 15. The number of triangles in this figure, of course. But then again, remember, we have more triangles on the outside. Let's just erase all this. We have our triangles on the outside, 2. So how many triangles are in this figure? Well, the number of triangles in this figure is just going to be equal to, we can use similar logic. There's going to be 3 of these lines, and we choose 2 of them to make a triangle. So there's going to be 3 choose 2 triangles here, which is 3. It's going to be 3, right? And then in this figure here, we only have 1 triangle, right? We only have 1 triangle in that figure. And then again, in the figure to the right, it's just again going to be 3 triangles, since we have 3 of the lines. So in total, we have 15, the original triangles, they got cut off, sorry, plus 3 from the left 2 triangle, plus 1 from the middle, 1 triangle, the triangle I marked earlier, and plus 3 from the rightmost triangle there. And then we add this up, we get 22. And then we have to also count the outside triangle, because the outside triangle adds 1 triangle. So the outside one gets 1 triangle. So we just add 22 plus 1 equals to 23, the answer. Now let's take a look at the next problem, number 13. There are 4 positive integers, a, b, c, and d. The first 3 numbers form an arithmetic sequence. The last 3 numbers form a geometric sequence, and the value of c is 3 times the value of a. Okay, so we want to find the smallest possible value of d. So then we have 3 numbers, arithmetic. Last 3 are geometric. And then c is 3 times a. So in order to solve this problem, let's just say that we have 4 slots, a, b, c, and d. So a, b, c, and d. Okay, so let's just say the first slot is a value of x, let's say. Okay, so the first slot has a value of x. Then the third slot, c, is going to have a value of 3x, right? Because the value of c is 3 times the value of a. And now we're given that the first 3 numbers form an arithmetic sequence. So the common difference between a and b, and between b and c, is going to be the same. So b will have to be 2x, so that the common difference between a and b is x, and the common difference between b and c is x. So by letting b be 2x, now we have that the common difference is always x between a, b, and c. Right, so now how can we continue? Well, we know that let me just erase this here to make it more clear. B, C, and D form a geometric sequence, right? So if B, C, and D form a geometric sequence, they have a common ratio. And the common ratio between B and C is 3 halves. The common ratio between C and D is again 3 halves. And this is just going to be 9 halves x. And we have to find the smallest possible value of d if there are integers. Remember, there are 4 positive integers, a, b, and c. So what is the smallest possible value of x such that all of them are integers? Well, the smallest possible value of x, x has to be a multiple of 2. X has to be a multiple of 2 because, only that 9 halves x will be an integer. And all these other values will also be integer from there. And the minimum multiple of 2 is just 2. So let's just say x is equal to 2. If we let x equal to 2, we get that d is equal to 9 halves times 2. So 9 halves times 2, because x is 2, which is 9. And similarly, plugging in the other values, 9 is the answer. But let me just show you, for the sake of showing the other values, this would be 6. This can be a way to check your work. It's not necessary, but could help you check your work. So 2, 4, 6, 9. Okay, so now we can just verify that 2, 4, and 6 form an arithmetic sequence, 4, 6, and 9 form a geometric sequence with ratio of 3 halves, and 6 is 3 times 2, so our answer is correct. So 9 is correct. And that can be good to check your work. Not sure if that would be worth it under the time conditions, but if you want to check your work, this would be an easy way to do so. Okay, so yeah, now let me just summarize the key steps in this problem. We have that A, B, 962C is divisible by 792. 792 is just 8 times 9 times 11. So that means this quantity has to be multiple of 8, 9, and 11. So in order for this to be multiple of 8, 62C has to be multiple of 8. And when will 62C be a multiple of 8? Well, we can see that 62C will be a multiple of 8 only when C is 4. So only for 6 to 4. C equal to 4. So it will only be a multiple of 8 for C equal to 4. So we can just plug that in right there. And no other values work. We can check that. And then from here, we look at the condition multiple of 9. So for multiple of 9 condition, we just add the digits up. We get A plus B plus 15 plus 9 plus 6 plus 2, 9 plus 6 plus 2 plus 4. Which means we just add them up. We get 21. So plus 21, this has to be a multiple of 9. A plus B plus 21. And we can subtract 18 off to get, because anyways we know 18 is a multiple of 9. So A plus B plus 3 has to be a multiple of 9. Meaning that A plus B can be 6 or 15. But then we look at the divisibility of 11 condition, we see that A plus 9 plus 2, so A plus 9 plus 2, minus B plus 6 plus 4 has to be a multiple of 11. So in order to do that, now what we need to see is that we need to see that, okay, so in order to actually approach this, we need to see that 9, 2, 6, 4, so we need to have the sum of the alternate digits, so A plus 9 plus 2, and the other digits, B, 6, and 4, they have to be off by exactly, they can either be equal, or they can be multiple 11 difference. So A plus 9 plus 2 is the odd sum, so A plus 11, and the even sum is B plus 6 plus 4, B plus 10. And these have to be equal, and what does that mean? Well, that means that A plus 1, well, sorry, they're not necessarily equal. A plus 11 minus B plus 10 has to be multiple of 11. And we can simplify this to get A minus B plus 1. And it can either equal 0, 11, etc. And we see that it cannot equal to 11. Because if it's equal to 11, then that means that A minus B has to be equal to 10. But that's not possible because A minus B can't be 10 because the maximum value of A is 9 and the minimum value of A is 0. So this will be at most 9. So this doesn't work. So that means this must be the only possibility, meaning that B equal to A plus 1. And then what we do is we substitute it in to each of these cases. We can do that. And we see that if we plug it into the first equation, we have A plus 1 equal to 6. Or 2A plus 1 is 6. But that's not possible because notice that this side is even and this side is odd. The second case, A plus C is 15. We have, again, A plus 1 equal to 15, meaning 2A plus 1 is 15, or A is equal to 7. So that's the answer. Let's now take a look at the next problem. How many positive multiples of 1001 have less than 15 factors? And again, for this problem, we have to say 1001 equal to 7, 11, 13. In order to get less than 15 factors, well, we have again 111 here. This number has 1 plus 1 times 1 plus 1 times 1 plus 1 factors equal to 8. And similarly, 8 is less than 15. So 1001 is one of the numbers that does work. Now there's other cases. We can also have 7 squared times 11 to the 1 times 13 to the 1, which has 2 plus 1. Remember the factor trick we learned in one of the previous classes? We use the same trick here. 3 times 2 times 2 equal to 12. Right? Okay, so again, 12 is less than 15, so this also works. And similarly, 7 times 11 squared times 13 to 1, and 7 times 11 times 13 squared these all do work because they all have 12 factors. So these are all good. So right now we have a total of 4 cases. But notice that no other cases work. So for example, we have that 2 times 1001. So 2 to the 1 times 7 to the 1 times 11 to the 1 times 13 to the 1 has 1 plus 1 times 1 plus 1. Oops. Times 1 plus 1 times 1 plus 1 factors. And this is equal to 16, and that's too much. And similarly, all other primes, they don't work. Another case that doesn't work would be, for example, 7 cubed times 11 to the 1 times 13 to the 1. And that also won't work because this case would have 3 plus 1 times 1 plus 1 times 1 plus 1 factors, which is going to be equal to 16. It doesn't work. So clearly, the answer is just 4 because you have 4 possibilities. Now let's take a look at the next problem. Okay, this problem was really tricky. Many of you got thrown off and put the answer of 18. Let me explain why. So we have Alice, Bob, Claire, Dave, and Emma around a round table. Alice refuses to sit next to Bob. How many different ways can they sit around the table if rotations are considered the same arrangement and are not considered different? So we have a circle, let's say we have 5 people. 3, 4, 5. And if you remember from the review class on Friday, we had that Alice, Bob, Claire, and Dave and Emma, we have to arrange them in a circle. And we can just assume Alice is always here because rotations are the same thing. So what we notice here is that if Alice is at this very center position here, Bob, Claire, Dave, and Emma, we have to put them around Alice. Okay, so let's use complementary counting. The reason is Alice refuses to sit next to Bob, and doing case work on that seems hard, so why not just find the total number of cases and subtract the cases where Alice is indeed next to Bob? So first of all, ignore this condition. How many ways is there? Well, again, you can assume Alice is here, and now we have Bob, Claire, Dave, and Emma to arrange. And in the review class, we have this is just going to be arranged in 5 minus 1 factorial equals to 24 ways, right? And the reason is you can just assume Alice always stays here, because when you rotate Alice to different positions, it's the same thing. And we can arrange Bob, Claire, Dave, and Emma in 4 factorial ways, so 24. Okay, so that's the total number of ways. So, okay, that's the total number of ways, right? So we have these 4 ways to arrange people, and we can also have different arrangements. So maybe Alice is here, and then Bob, Claire, Dave, and Emma are around the circle. Right? We can have something like that too. That would also be perfectly fine, right? So we have that would also work. So these are both possibilities that would work, and because rotations are considered the same arrangements are not considered different. Then we know that these 2 arrangements are the same essentially. Because rotating it is not doing anything. We're still having the people around. Hopefully that helps some of you understand better why. Okay, so now back to the original problem. Alice cannot sit next to Bob. So what if Alice does sit next to Bob? Okay, so if Alice does sit next to Bob, then it'd be something like this, right? Where Alice is there and Bob is there. So how many ways is there in this case, right here, that I just drew? Claire, Dave, and Emma could go here. So Claire, Dave, and Emma go here, and Alice and Bob go here. This is going to be arranged in 3 factorial ways, right? Because you can assume Alice and Bob are there. So 3 factorial ways to arrange them equal to 6. And these 6 ways don't work. We have to subtract them from 24 that we found. Because Alice cannot sit next to Bob. This is not allowed. Subtract 6, right? But a very common mistake was just say, okay, the answer is just going to be 24 minus 6 times 18 equals 18. And a very common answer I saw from yesterday from people was they just put 18. But that's not true. And the reason is we have to subtract extra. Bob can also go on the other side. And it will still be next to Alice. And that was something thing many people forgot. So Bob can be on Alice to the right, or Bob can be on Alice to the left. There's two different cases. And then from here, it's the same thing. We have Clara, Dave, and Emma to be arranged here. This is again another 3 factorial equal to 6 ways that don't work. Right. Okay, so then we just do 24 minus 6 equal to 12. So 12 is the answer to this problem, not 18. And be very careful about the cases you have to subtract. So Bob can go on both sides, and that was something that many people missed, so be sure to be on the lookout for next time. And now let's move on to the next problem. Okay, so this problem was, it seems very intimidating, right? With all the cyclic quadrilateral and all the different angles, but really it's a really nice and simple solution. So A, B, and C form an arithmetic sequence, right? So we have A, B, and C form an arithmetic sequence, meaning, right? But what we notice is that A, B, and C, the angles, they're in a triangle, right? They're in a triangle. Meaning that A plus B plus C equal to 180. So if A plus B plus C equal to 180 degrees, and they form an arithmetic sequence in that order, B is going to be the middle term. B will be the middle term because it's a center term, and we're formed in that order. So B will have to be the middle term. And since there are 3 terms in the arithmetic sequence, the middle term is just the average of the terms. So B will be equal to 180 divided by 3 equals 60. And if B is equal to 60, then let's just mark that here, 60 is great. Because, again, the middle term is going to be the average of all the terms. And sum is 180, so we divide by 3 to get 60. Okay, so now we know the B is 60. Now let's take a look at the second condition, P, Q, and R. Second condition. So this condition is actually really similar. P plus Q plus R is again 180. You have P, Q, and R here, and they're a triangle. And they also form an arithmetic sequence. So what does that mean? That means the middle term is going to be equal to Q is 180 divided by 3 equal to 60. So Q is going to be 60 degrees here. Okay, so now that we know these two are 60, let's deal with the last condition, right? The last condition, B, C, and R forming an arithmetic sequence. So B, C, and R form an arithmetic sequence. Let's just say C is 60 plus X, and R is 60 plus 2X. Because we have B, C, and R. If B is 60 plus X, C is 60 plus 2X. No, sorry, it should be 60. It should be 60 plus X, and 60 plus 2X. Right? Each time they add X. So they form an arithmetic sequence, as I drew in the diagram. So what does this tell us from here? Since the sum of angles C and R, angle C plus angle R, is going to be 180 again, because angles C and R are supplementary. Okay, so if angles C and R are supplementary, C, we just let X be 60 plus X plus 60 plus 2X. Meaning the sum is 120 plus 3X. And that sum, since the angles are supplementary, is 180. Meaning that we subtract 120 from both sides, we get 3X equal to 180 minus 120, which is 60. And that means that X equal to 60 divided by 3 equal to 20. Okay, so if X equal to 20, then what can we do from here? Well, we need to find the value of A. So again, let's substitute our values of X here. So this will become 80, right? C will be 80. And if C is 80, and then we know A plus B plus C is 180. We don't even have to write it out, yeah. So you see A plus B plus C is 180, meaning that this value will be 40. A will be 40, so 40. Because 60 plus 80 plus 40 is 180. And that was a very nice solution there. Okay, so number 18, I'm going to explain a different solution than Professor Lowe did, because he explained away using binomial theorem, but I'm going to explain away using choosing and the techniques that we learned. So we have a set 1, 2, 3, 4, 5, 6, 7. How many sets are there? So the sum of the elements are even. So notice that, let's break it up into 2 different sets. 1, 3, 5, and 7. We're breaking it into 2 different subsets. And 2, 4, and 6. 2, 4, 6. So now we've broken up into two different subsets. We want the sum of all the elements we choose to be even, right? Okay, so notice something here. Whenever we add even elements together, they're even. So 2 plus 4 is 6, for example. 6 plus 6 is 12, for example. So whenever we add any elements from here, we get an even sum, right? So we can really choose any elements from here. So there's 2 to the 3 ways of choosing elements from 2, 4, and 6. Because it doesn't matter what elements you choose from 2 to 6, 2, 4, and 6, there's going to be 2 to the 3 ways to arrange them. And the sum of these elements will always be even, no matter. Or actually, that was not a very good way to start. Let me have started from, I should have started from here, the 1, 3, 5, 7. Because you notice that these elements will always sum to even sum. And since some of the even elements will be even, some of the odd elements should also be even. So some of any combination of these odd elements has to be even, meaning that out of these 4 elements, we can either have to choose 0 even elements, or we can choose 2 even elements, or we can choose 4 even elements. And that will result in the sum being even, the sum of these numbers being even. Okay, so, and just to be clear, the reason is, but when we add an odd number and an odd number, we get even number. When we add 3 odd numbers, we get an odd number again. So the number of odd numbers we add has to be 0, 2, or 4. Because the sum of 0 odd numbers is 0, the sum of any 2 odd numbers is even, and the sum of all 4 odd numbers, well, you can calculate it, it's just 16, which is again even. So you have 4 choose 0 plus 4 choose 2 plus 4 choose 4, which is equal to 4 choose 0 is 1, 4 choose 2 is 6, 4 choose 4 is 1, meaning the total sum is 8. So there's 8 ways to choose elements from 1, 3, 5, 7, and from 2, 4, 6, right? We have 2, 4, 6. We have 3 elements, so there's going to be 2 to the 3 ways to arrange them. So equal to 8. So total there's going to be 8 times 8 equal to 64 ways. Except again, remember here, pay attention to the wording of the problem, as that can throw you off completely. Remember, from the review and strategies, whenever you get an answer, you should always make sure your answer is what the question is asking. So how many non-empty subsets? And the empty subset with nothing in it has just nothing in it, right? So the sum is just going to be 0, which is even. So we must subtract that case off to get 63. Now let's take a look at the next problem. Okay, this problem was tricky a little bit, but it really, the solution is not that hard. Okay, so just to clarify some things here. Let me just clarify some things here. Yeah, so basically whenever you add these numbers, so for example, when you add 2 odd numbers, you get even number. When you add 4 odd numbers, any 4 odd numbers, you always get even number. But when you add, let's say, 3 odd numbers, so 1 plus 3 plus 7, you get an odd number. So this will always be odd. And then for the second set, let's say you add some numbers, so 2 plus 4 plus 6. So whenever you add any combination of even number is even, and even plus even is even. So whenever you add even numbers, the sum is even. So hopefully that clarifies any confusion that was there in this problem. So 8 times 8, 64, minus 1 equals 63. Okay, so now let's move on to the next problem. Brian chooses a number between 1 and 1,000. So there are 1,000 possibilities, right? So the number has no prime factors greater than 5. The number is not a perfect power. And the number has 6 factors. And this last condition doesn't really seem to mean anything. What does that really mean? Well, we'll worry about that condition at the end. But a good strategy is when you have a bunch of conditions, a general problem solving strategy that's come up numerous times on AMCs, is when you have a bunch of conditions, look for the conditions that are either the most restrictive or the easiest to work with. So the one that gives you the most information, the most things you can try to extract from it. So in general, for this problem, we have 4 different conditions, and it's just all over the place. What does that even mean, really? So let's look at the least restrictive, or the condition that's going to be easiest to work with. And that's going to be the first condition. Since that completely eliminates any number without 2, 3, or 5. So now we know our number must have only prime factors of 2, 3, and 5. Okay, the number is not a perfect power. So the number cannot, or n, let's say n. N cannot be something like 3 to 11 or something. Because that's a perfect power. Or even something maybe like 3 to 5, because that's also a perfect power. So those don't work. That's what I mean by perfect power. Well, this condition looks like it's going to be easy to work with. We have 6 positive factors, right? So since it has 6 positive factors, this looks like we can work with it somehow. So remember the factor trick? In order to get 6 factors, we either have 1 6, or we have 2 times 3. So for 1 6, what does that mean? Well, that means we have something of the form p to the 5, t1 to the 5, right? Or so, it's any p to the 5, because this will have 5 plus 1 equals to 6 factors. What about 2 times 3? Well, in order to get 2 times 3, we would have to have p1 to the power of 1 times p2 to the power of 2. And since we have these two conditions here, that means that this will have 1 plus 1 times 2 plus 1 factors equal to 6 factors, right? And I can see this repeated theme of factor trick. It's very important, so that's why I've included it so many times today. So 1 plus 1, 2 plus 2 equals 6. So that means we have 6 total possible factors in this case. So now, what are the different possibilities, really? So p to the 5, what can p to the 5 be? P to the 5 can be maybe 2 to the 5, could be 3 to the 5, or 5 to the 5, right? None of the other ones work. So you have 2, 3, and 5 prime factors. But what do you notice about this immediately? They don't work. Why? Because it's a perfect power. These are all perfect powers, so this case itself doesn't work. The second case, however, and you didn't actually have to do this, you could have just directly eliminated p to the 5, because we know that it's perfect power. So that was a little bit unnecessary, but I wanted to make it clear how exactly this case doesn't work. So that's why I just listed the possibilities there. And we have the condition here. Okay, so here, what we would do is you see that, okay, we can have 2 to the 1 times 3 to the 2, 2 to the 1 times 5 to the 2, right? Since 2, 3, 5 prime factors. Or we can have something else. You get 3 to the 1 times 2 to the 2, or 3 to the 1 times 5 to the 2. And then you can have 5 to the 1 times 2 to the 2, or 5 to the 1 times 3 to the 2. Meaning that the numbers are 18, 50, comma, 3 to 1 times 2 to the 2 is just going to be equal to 12, comma, 75. 5 to 1 times 2 to the 2 is 20. 5 to 1 times 3 to the 2 is 45, right? So I just evaluated to these expressions. And now we're given the last condition. So again, the problem solving strategy, the idea here is you look for the most restrictive conditions to work with first, and then after that you narrow it down to the conditions that may not give you as much. So look for the conditions that tell you the most and the most restrictive in the beginning. Okay, so now look at the last condition, remainder of 5 when divided by 7. So the first number leaves a remainder of 4 when divided by 7. This number leaves a remainder of 1 when divided by 7, since 49 is a multiple of 7. 12 leaves a remainder of 5 when divided by 7, so this works. 75 leaves a remainder of 5 when divided by 7, so this works also. 20 leaves a remainder of 6 when divided by 7, so this doesn't work. Just cross these out. 45 leaves a remainder of 3 when divided by 7, so that doesn't work. So overall we have 12 plus 75 equals 87, the answer. Okay, now let's move on to the next problem. Jill has a container of water with a cylindrical bottom and frosting-shaped top. She fills it completely with water and hikes up the hill with Jack. When she reaches the top, she drinks 350 pi, and Jack drinks 500 pi. What is the height of the remaining water in the container? So for this problem, the idea is, let's first find the volume of the frustum at the top. So notice that since this length on the bottom is 20, this whole thing is 20, right? Each of them will be 10 here. And if each of them are 10 here, each of these will be 5 here. Okay, so what is the volume of the frustum now? Well, this will be 6, right? So if that's 6, now we can form similar triangles, right? We can form some similar triangles here. So as you can see here, this length here on top will have to be 6 too. this has to also be 6 since this is 6. Since the ratio of 6 to 5 has to be equal to the ratio of the long leg 12 to 10. Okay, so then from here, how can we find the volume of the frustum? We can just find the volume of the big cone and subtract the volume of the little cone. What's the volume of the big cone? Well, we can use our volume formula as pi times 10 squared times 12 divided by 3. We get 400 pi. The volume of the little cone is just going to be pi times 5 squared times 6 over 3, which gives us 25 times 2 equal to 50 pi. So overall, we have 350 pi as the volume of the frustum. And then from here, 350 pi. From here, we see that, okay, Jill anyways drinks 350 pi. So Jill will just drink the volume of the frustum on top. So let's just get rid of all this. So Jill will drink the volume of this top frustum here. And now Jack drinks 500 pi. So let's just say that Jack drinks till a height h. So let's say Jack drinks till a height h here. Whoops. So Jack drinks till a height h here, right? So if Jack drinks till a height h there, then we know that the volume of what Jack drank is 500 pi. And since the radius of this circle is 10, we know that the volume of the cone that Jack drank was pi times 10 squared times h equals 500 pi, because again, he drinks 500 pi. And this h is what we want to find that he drinks. And you can imagine, just if you have a cylinder here, the very top part of the cylinder, that top part of the cylinder is going to be what Jack drinks. We can solve this equation I just wrote down. We get 100 h pi equal to 500 pi, meaning that 100h equal to 500, or h equal to 5. And then we can say that, okay, this is 5. And then here we see, so the height of the remaining portion is just going to be 40 minus 5, or 35. Okay, so now we're going to move on to our last 5 problems. So I'm actually going to skip these 2 problems for now. I'll come back to them at the end. The matrix below consists of rectangle ABCD such that this mass below is AD is equal to 3, and we drew 220-degree arcs such that the midpoint of AB and midpoint of CD, respectively, are shown. The shaded mask is the area of n pi, find n. So this problem, it's not, you just draw this line here, it's going to be 3, and then we have some 30, 60, 90 triangles. And then from here, what we do is we say this is 3 root 3, but that's actually not needed, this is 6. And the area of this mask turns out to be a really nice result. It's going to be this area here, on the outside. So it's going to be the area of that purple shape there. That's going to be the area of one of the sectors. And then there's also an area of the other sector here, right? And the area of this one sector too. So what is the sum of the area of both of these sectors? So the area of the purple sector is going to be pi times 6 squared divided by 3, since it's a 120-degree arc. So let me make that up here. Pi times 6 squared times 120 over 360, which is equal to 36 pi by 3, equal to 12 pi. The area of one of the arcs, and since there are 2 of them, we multiply by 2, so you get 24 pi, the area of both arcs. But then remember, you might be thinking, oh, we're overcounting this region in the middle. We're overcounting this region in the middle right here. But then we're also undercounting this region on the outside here. We're not even counting that at all. And the idea here is to notice that, let me just mark it with the pen here. So this area of this triangle here is going to be the area of this triangle here. It's equal. And the area of this triangle here, the area of this triangle here is equal to the area of this triangle here, as I drew. So that means the area we overcounted and the area we didn't count is equal. So that means the answer is just going to be 24 pi, and that means n is 24. Oops, 24. And many people during the competition were asking, wait, how is it only n pi? Why is there nothing else we have to add? And then the idea is, the reason we don't add anything is because the extra area the extra area on the outside is equal to the area we overcounted. So we're good here. And we really just have to add the areas of the two arcs. And this turns out to be a really, really nice answer. No other terms, like there's no n pi plus extra stuff. So this is a nice one. Oh yeah, and this problem was interesting in the sense that it seemed super complicated, but the solution is super easy. So this problem, even though it seemed like one of the harder problems of this test, it seemed like pretty hard, it actually has a really nice and easy solution. So we have 19 acorns, and we have to distribute it amongst these 3 squirrels. So what most of you probably did is most of you who solved it probably was casework. You just do the different cases, and that's totally doable. But there's a really nice solution to this problem. So the first squirrel 1, let's just say the squirrel 1, since it wants a positive odd number of acorns, has 2a plus 1 acorns, where a is a number 0 or more. So a can be a non-negative or 0 or more. And then the first squirrel wants 2a plus 1 acorns. The second squirrel wants, okay, so let's take a short break now. I'll complete the solution later. Let's take a short, maybe 2 or 3 minute break. And if you haven't already filled out the Raffle form and prize form from yesterday, please make sure to fill it out today in order to be counted in the raffle. And the raffle form should be sent to chat again if you didn't fill it out yesterday. Because it looks like some of you are putting some really great ideas of how to solve this problem using stars and bars. And that is actually the correct way. And it's very simple, actually. Put some ideas in the chat that we can use stars and bars, and that's actually true. So the second squirrel is fine with any non-negative even number of acorns. So the second squirrel is fine with 2b. The third squirrel insists he must get an even number of acorns greater than or equal to 4. So the third squirrel insists on something like 2c plus 4, where c is 0 or more. Because greater than or equal to 4, right? An even number greater than that. So 2c plus 4. And second one will be 2b. Right? Okay, so now we have the sum of all these three values is going to be 19. So that means that 2a plus 1 plus 2b plus 2c plus 4 equal to 19. Meaning 2a plus 2b plus 2c equal to 19 minus 4 minus 1 equal to 14. And now we can just divide by 2. So a plus b plus c equals to 7. Meaning that since we have three, you can think of three buckets, A, B, and C. We can think of like three buckets like that, A, B, and C, to give the 7 to these three buckets, kind of. And we can do that in 9 choose 2 ways, because we have 7. We can just think of 7 dots, 1, 2, 3, 4, 5, 6, 7 dots. And we have 2 bars for the 8 to distribute them into 3 groups. And we can arrange this in 9 choose 2 ways by stars and bars. So this solution is really simple using stars and bars, which gives an answer of 36. So there's 36 ways to distribute the acorn. And as you can see here, solving this problem required a little bit of ingenuity, and the idea was to think of, oh, well, it's a distribution, and we have these conditions, so why not just let it be this value here, and then find a stars and bars equation to solve. Okay, so now we went to 25, and Professor Lowe gave a very nice complementary counting solution, but I'm going to show you a different solution using direct casework. So the Blazers record stands are playing 7 games. The team wins if they have won 4 games, and no more games are played after that. Both teams have equal likelihood of winning a game. The probability the court stands win the series and lose less than 3 games can be expressed as m over n, find n plus n. So again, I'm going to do this using direct casework. So it's actually really not that hard. It's about the same difficulty as complementary counting. So in order for the court stands to win 4 games, there's 2 cases really. 3 cases really. Either the court stands can win all 4 games, right? Or, so what is the probability of this happening? The probability of this happening is just going to be equal to, well, 1/2 to the 4. Right? Because there's a 1/2 chance, equal likelihood. The next case is where you have a Blazer win. So let's see something like court stands, Blazers, court stands. Something to remember here is that the last game has to always be court stands win. Because if court stands don't win the last game, after court stands win, the Blazers, after the court stands win the series, there's no more games. Blazers can't win any games after the court stands have already won the series, right? So that means the last game has to always be court stand win in the series in order for this to be true. And then, okay, so what's the probability of this exact sequence happening? This exact sequence that I just wrote. Well, there's a 1/2 to the 4 chance of the first 4 values happening times a 1/2 chance that the last one will be a 1/2. So this is going to be equal to 1 over 32, right? And if you know that that's going to be 1 over 32, then we multiply by the number of ways of arranging these 4 letters. So we can arrange these 4 letters, right? Because this is not the only way. We can arrange these 4 letters in any way we want, so times 4 equal to 1 over 4 over 32. And I'm not going to simplify it. You'll see later why, because it's going to be easy to add. So then you have the last case where the Blazers win 2 games. That would be something of the form court stands, Blazers, maybe Blazers, again, court stands, something like this maybe. So again, what's the probability of this exact sequence happening? That's going to be equal to, well, the first 5 games are going to have a 1/2 to the 5th chance of happening. And then the last game, again, has to always be court stands. It has a 1/2 chance of happening. And this gives us 1 over 64. But then again, we multiply by the number of ways of arranging the sequence in the beginning. And how many ways can we do that? We have 5 letters. We choose 2 of them to be Blazers. So if I choose 2 equal to 10 over 64. If I choose 2 is just 5 times 4. 5 times 4 divided by 2 times 1 over 64 equal to 10 over 64, which is 5 over 32. Meaning that we add all them up. This is 2 over 32 plus 4 over 32 plus 5 over 32 equal to 5 plus 4 plus 9. 5 plus 4 plus 2 equal to 11 over 32. So the answer is 43. Let's now take a look at 20 and 21 that we originally skipped. 21 and 22. So 21, we have a grid in an infinite coordinate plane. So we're standing at point 0, 0 in an infinite coordinate plane. Let's draw that out. Infinite coordinate plane right here. I'm going to draw this grid here. So we have 2 of these lines here. Right, so this is 0, 0. 3, 3. We want to go from 0, 0 to 3, 3, right? On any given move, there's a 1/3 chance of moving up. So a 1/3 chance of moving up. Sure, I should have said that first. 1/3. There's a 1/3 chance of moving to the right. There's a 1/6 chance of moving down. And a 1/6 chance of moving to the left. So I now drawn all the different possibilities. The probability of reaching 3, 3 in less than 8 moves can be described as A over 3 to the B. Find A plus B. Okay, so in order to solve this, what we realize is that we need to do a little bit of casework here. The first case is just going to be 3 right steps, and then 3 up steps. Okay, so what's the probability of 3 right steps and 3 up steps happening? What's the probability of this exact sequence? Well, there's going to be a 1/3 chance of the right happening times power of 3. So there's a 1/3 chance of these 3 rights happening. And then a 1/3 to the 3 chance of these 3 ups happening. Since there's a 1/3 chance of each of the 3 ups happening. So this gives a total of 1/3 to the 6 equal to 1 over 7 to 9. Cool. But then I said for this exact sequence, right? What about rearrangements? We can rearrange these terms in the sequence in 6 choose 3 ways. 6 choose 3 is 6 times 5 times 4 divided by 6 equal to 20. So we have 20 over 729. Okay, good. Next, what are the other possibilities? We can also have, here's where it gets a little bit tricky. So a sequence, for example, as I just showed, is going to be something like of the form this, right? Something like this maybe, right? So that's a regular sequence with only 6 moves. What about, since we can have less than or equal to 8 moves, so we can have a little bit more than 6 moves too. So if we can have a little bit more, alright, I don't think it would have been worth expanding it. Let me just leave this as 3 to 6. Yeah. Okay, so we have this path here, right? And we don't actually need such a path. So let me just go back here quick. This should be 3 to 6. There's no need to write 729. So as I just showed a path here, we can also take a diversion path. We can go something like this. Oops. We can go something like this. Then you can go to the left 1. Then you can go up. Then you can go right 3 steps. For example, you can go something like this too. Or maybe that's not so clear on the blue, so let me just do purple again. Something like this. Let me just go all the way there. And if you count this out, we have 1, 2, 3, 4, 5, 6, 7, 8 moves. So less than or equal to 8 moves. This does count. This is 8 moves. This is an 8 move path. And as you can see here, the reason it's 8 moves instead of 6 moves is because we took a diversion. We took a left step and then we accounted for it by taking a right step. So now we can see the sequence here is going to be left, right, 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 U, U, U. Okay? So left, right, 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 U, 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 U. We'd have, that's one possible sequence. Right? That's one possible sequence that has 8 moves. And notice that 7 moves is not possible. Since if you take a divergent path, we have to come back. So 7 moves is not possible, but 8 moves is possible. Because if you take one left step or one down step, then we need to come back, right? We need to come back. And that will take an additional step. So we can only increase our move count by 2. We cannot increase it by 1 and get 7. So in this sequence here, what's the probability of this exact sequence happening? Well, there's a 1/6 chance of the first step being left times 8. What's the probability this will be right? 1/3, right? So 1/3 chance of each of the right steps being there to the power of 4. There's a 1/3 chance each of these 4 steps will occur times 1/3 to the power of 3 for the up steps. Right? And this is equal to 1/3 times 1/, let me just put that in a different way. So we have equal to 1/2 times 1/3 times 1/3 to the 4th times 1/3 to the 3rd. This is equal to 1/2 times 1/3 to the 1/3 times 1/3 to the 4th times 1/3 to the 3rd equal to 1/3 to the 1 plus 1 plus 3 equal to 1/3 to the 8. Okay, so now this is the total probability of this exact sequence happening. But then again, we have arrangements, right? We can arrange this word in a certain number of ways. So how many ways are there to arrange this word? Because again, we don't have to necessarily have those steps in that order. We can flip them around, we can move them, arrange them. The probability of that, well, how many ways can we do that? Well, by the word rearrangement formula taught in one of our previous classes, we have 1, 2, 3, 4, 5, 6, 7, 8 letters, so 8 factorial, divided by the 4 r's, so 4 factorial, the 3 u's, so 3 factorial, equal to 8 times 7 times 6 times 5, and then the 4 factorials will cancel, over 3 factorial 6, 6 is cancelled, we're left with 8 times 7 times 5, which is 56 times 5, or 280. So the overall, this is the probability of one of these sequences happening. We multiply by 280 to get the probability of all sequences of this type happening. And there's a very symmetric case. And that is going up and down. So up, down, up, down, up, or let me write that better, right? Down, up, up, right. So let me take a look at the questions. Okay, so let's continue. So here we have a sequence, and this is very similar to the first case. These cases are very similar. So the idea here is not since these exact same probabilities. Again, there's going to be a 1/6 chance of the first down being there times a 1/3 to the there's 4 up steps, so 1/3 to the 4 chance times 1/3 to the 3 of the right steps right? And that's equal to 1/2. Again, the same thing earlier. I'm not going to really do the calculations all over again, but it's equal to the same quantity. 1/2 times 1/3 to the 8 times 280, right? So now what can we do? Now we just need to add all our probabilities up. So now in order to add all the probabilities up, let's just do 20 over 3 to the 6, so 20 over 3 to the 6, plus, well, 180 times 280, 1/2 times 280 is 140. So plus 140 over 3 to the 8. And again, this is the same case as earlier. So again, it's going to be 140 plus 3 to the 8. Okay, so it seems like there's some confusion about why this is going to be 8 steps, but the reason is basically when you go left and right, we have to take a left and then a right, and when you go up and down, we have to go up and then a down. So those are just diversions. You can think of them as a diversion. And we need either, to get 8 moves, we need 1 diversion, left, right, or up, down. And to get 7 moves is not possible. In 6 moves, we have 0 diversions, just only right and up, getting straight to 3, 3. Okay, so again, continuing on with our calculations here, we have 20 over 3 to the 6 equal to 20 times 9 over 3 to the 8. So 180 over 3 to the 8. Plus 140 over 3 to the 8, plus again 140 over 3 to the 8. And adding these all up, we get, well, 180 plus 140 is 320, 320 plus 140 is 460, so 460 over 3 to the 8. Meaning our answer, well, we want 8 over 3 to b, so 460 plus 8 equals to 468. And that's your answer. Nice. Okay, so are there any questions on this problem? Because this is a really tricky problem. Okay, now let's continue on for this problem. So Eric is stacking 26 Jenga blocks. For n greater than 1 equal to 1, the probability that placing the nth block causes the whole tower to topple is 1 over 26 minus n. Assuming the tower still stands after placing n minus 1 blocks. Okay, so what's the expected number of blocks placed before the block that causes the tower to topple? Okay, so we have 26 Jenga blocks for n greater than or equal to 1. The probability the nth block is 1 over 26 minus n. And okay, many people were saying yesterday that, oh, for n equal to 26, it's just going to be 1 over 0, undefined. But the reason we don't even have to worry about that is because for the 25th block, n equal to 25, we have 1 over 26 minus 25 equal to 1. We have a guarantee, that means we have a guarantee that the 25th block will topple. Meaning we don't even have to worry about the 26th block at all. So that's why we don't have to have something like that. Okay, so as you can see here, we're going to now take a look. Now we're going to solve this problem. We're now going to solve this problem. So let's start off from the beginning. Let's make a table here. So probability topple of the block will topple. Let me just write block topple probability. P of block topple. And then we have P of block standing, so it will remain standing. And now I'm going to construct a table here, Okay, so for the first block, what's the probability the first block will topple? Okay, sorry about that. What's the probability the first block will topple? It's going to be 1 over 26 minus 1 equal to 1 over 25. Right? 1 over 25 chance the first block will topple. So what is the probability the first block will remain standing? 24 over 25. Oh. Okay, so now, what's the probability the second block will topple? That's just going to be 1 over 24, right? And the probability the second block will remain standing is 23 over 24. Except, oh, sorry, I'm a little bit unclear here. I meant tower standing and tower topple, not top block. So tower standing, tower topple. Whoops. Okay, so that should be good now. So I mean the whole tower up to that point, not just the block. So the block standing you already know, the tower topple up to that point. Okay, so as you find here, there's a 1 over 24 chance the second block will topple, cause the tower to topple, and 23 over 24 chance the second block will cause the tower, will still keep the tower standing. Except, in order to have the second block keep the tower from toppling, we need to have the first block not topple. So we need to multiply this here and this here. So 24 over 25 times 1 over 24. The reason this is because we can only place the second block if the first block remains standing. So only if the first block remains standing can we even place the second block. So there's a 24 over 25 chance of placing the first block will be placed without toppling the tower. And then from there, there's a 1 over 24 chance the second block will topple. And then for the second block tower remaining standing, 24 over 25 chance the first block will remain standing. From there, a 23 over 24 chance that the block will remain standing. And we multiply these together to get the 24s cancel, we're left with 23 over 25. And this is equal to 1 over 25. Right? Okay, so as you can see here, now in order to solve this problem, what we need to do is, since you have 24 over 25 times 1 over 24, 24 over 25 times 23 over 24, chance the tower will remain standing here, and tower will topple here. What about the third block? Right? So again, with the third block, the probability that the second tower will topple is just going to be equal, well, probably the second block will topple will just be 23 over 25. So the probability the second block will remain standing, both the first and second blocks will remain standing is 23 over 25. And then from there, we multiply the probability the third block will cause the tower to topple, which is 1 over 23. That cancels out, we get 1 over 25. And then again, for this one, we multiply the probability the block will fall, which the third block won't fall, times the probability the first two blocks won't fall. That's 22 over 23 equals 22 over 25. So do you notice the pattern here? Do you notice any pattern here? And here's a hint. 1 over 25, 1 over 25, 1 over 25 chance. 24 over 25, 23 over 25, 22 over 25. Do you notice the pattern here? The pattern is just that, you see here, it goes down by 1 each time. And this tower topple remains static, same. So let's just do dot to dot all the way till 24. Okay, so for 24, what is the probability it will topple? Okay, so 24, just like earlier, the probability that it won't topple, so 24, probability the 23rd block won't topple is 2 over 25. So it's just going to be 1 over 25 again by the same pattern. 1 over 25, 1 over 25, 1 over 25. And the probability the 24th block will remain standing is 1 over 25 again. Because each time it reduces by 1. For the first block remaining standing, there's a 24 over 25 chance it will remain standing. For the second block, there's a 23 over 25 chance. And each time it reduces by 1. So once we get to 24, we'll have reduced it 23 times by 1 over 25 to get 1 over 25. Okay, and then for 25, for the 25th block, the tower here would be, well, what are the probability that the 25th block will cause the tower to topple? Well, that's just going to be 1 over 25. There's going to be a 1 over 25th chance that the tower will remain standing up till that 24th point times 1, the probability the 25th block will topple, right? Because 1 over 26 minus 25 equal to 1. 1 over 1. So the 25th block has a guarantee of toppling, meaning that the 24th block has a 1 over 25 chance of staying standing, and the 25th block will guarantee to topple, so the probability will topple here is 1 over 25 times 1, and here's just 0 since it's guaranteed to topple, and there's no chance it will remain standing by this time. Okay, so now we want to find the expected number of blocks placed before the block that causes the tower to topple. So for this, in order to do that, what we do is we see that, okay, what is expected? What is the probability that 0 blocks will be placed before it topples? Well, the probability that it will topple on the first block. Okay, so here's the idea here. Since it will topple on the first block with probability 1 over 25, that means that 0 blocks, the probability of 0 blocks being placed is 1 over 25, right? Because if the first block causes the tower to topple, 0 blocks are placed before the block that's placed causes the tower to topple. So the next block, for block 2, again, right here, we just do, okay, if the second block is the one that causes the tower to topple, then the first block is the one that's placed before the tower topples, times 1 over 25th. And we will do the word ceremony at starting 5:30, and the raffles at 5:30. So make sure to stay till there. We're almost done with this problem. So if the second block causes the tower to topple, there's a 1 over 25th chance the first block is the one that causes the tower to topple. And we keep going. This is going to be 2 times 1 over 25th. Because there's a 1 over 25th chance the third block causes the one to topple. Okay, it looks like some of you are getting a little bit confused. So basically, just to summarize, the idea here is we found this table, which was not that bad. And then from there, the expected value is basically just the average. You can think of it as the average, expected number. You can think of that as the average. And we want to find the number of blocks standing before the block causes it to topple. So if you want to find the number of blocks placed before the top block to topple, the expected number is just going to be basically the expected value of something is just the probability of each of those outcomes happening times the number of blocks that will remain standing. So for a number, let's say 2, the probability that the expected value is 2 is 1 over 25. The probability the expected value is 1 over 25. So we just add all these values up. Plus 3 times 1 over 25. Plus 4 times 1 over 25. So on. all the way till 24 times 1 over 25. And as you can see here, the problem here is very interesting because we have a bunch of telescoping. These terms just cancel out like rapidly. There's so much telescoping. And if you looked in the previous class, telescoping is just mass canceling. So everything just keeps getting canceled. And then we add all these values up to get 24 times 25 divided by 2 equal to 12 times 25. And then times 1 over 25 equals 12, which is the answer to this problem. And I know the same solution seems a little bit complicated, and so now I'm going to show you a way you can somehow have guessed the problem correctly. So if you didn't know how to solve it, which most of you probably didn't know how to solve it, here's the way you probably could have guessed the answer correctly. So basically the idea here is you see that, okay, there's a 1 over 25th chance of the first block toppling, and so on, right? We have this table here. So a way to guess it is to think like, okay, so remember that the 25th block is guaranteed to topple. So even if it goes up to 24, the maximum is 24, right? The maximum is 24. And since the maximum is 24, the minimum is 0, right? The minimum is 0. The maximum number of blocks that can be placed is 24, because after the 25th block, it's guaranteed to cancel. There's a guarantee that the 25th block will topple, will cause the whole tower to topple. And that means that you can guess that, oh, it's going to be the average. It's going to be the average of this. So it's going to be 12, the average. You can think, okay, the average is 0 and 24. The average of the minimum and maximum is 12. So 12 is the answer. Okay, so that's the answer to this problem. We're now going to move on to raffle prizes. So let's move on to raffle prizes. So the raffle winners for the Wolfram and the Wolfram subscriptions. And as you can see here, the raffles for the Wolfram subscriptions. So the winners of the raffle, the winners will be posted in the chat right now. And the raffle prizes were 1 daily challenge course by Potion Low and 2 Wolfram notebook subscriptions. The raffle winners have been posted in the chat. Are being posted in the chat right now. Congratulations to all the raffle winners. And now we're going to move on to the honorable mentions. So here, thanks to the sponsors, we're going to be raffling a daily challenge course to Wolfram, and the winners are being put in the chat right now. And thank you to all our sponsors for helping this event. And now let's move on to the honorable mentions for 21st to 30th ranks. Here are the honorable mentions, the people who got 21st through 30th rank. Congratulations to everyone who got 21st through 30th rank out of everyone here. And then we also have honorable mentions from people who got 11th through 20th rank. So congratulations to all the 11th through 20th rank people as well. And also congratulations to all the 6th through 10th place people. Okay, so now let's move on to the top 5 who will be getting prizes for today. So fifth place, congratulations to Ray Zhao, and we'll be emailing you a $10 Amazon gift card and a MapleSoft student license. And then the 4th place winner is Benjamin Jang. We'll be getting a $15 Amazon gift card and a MapleSoft student license worth $99. The 3rd place, Jahai Lu, will be getting a $20 Amazon gift card and a Brilliant subscription worth $150. Whoops, it looks like my thing was being blocked. The thing was being blocked a little bit. So, congratulations to all the people. And also congratulations to Vincent for getting 2nd place. And he will be getting a $25 Amazon gift card and a Brilliant subscription worth $150. And also congratulations to 1st place, Fyodor, for getting 1st place with a score of 23 out of 25 problems correct. And he will be getting a $30 Amazon gift card and a Brilliant subscription worth $150. Congratulations to all the winners, and thank you for coming to this event and this competition here. Hope you all enjoyed this today, and we'll also be doing a future AMC 10 level class, so be sure to join in on that too. And again, thank you for all for coming to this thing. discussion is you now are allowed to discuss the problems from the competition. And thank you all for coming now. Okay, so just to be clear here, so the honorable mentions were 21st to 30th rank. Here are the honorable mentions for 21st to 30th rank. Here are the honorable mentions for 11th through 20th ranks. Here are the honorable mentions 6th through 10th rank. And here are the winners for the competition. Congratulations to everyone who participated in the competition, and I hope you all enjoyed it. And we'll also be doing a future AMC 10 class, so good luck to all of you on the AMCA who are taking it in the following link.